Looking at the 2014 AP Calculus exam, number 5, we have a table of values for f and g. They do tell you that both are twice differentiable, which is important. It means theorems can be used. First, find the x-coordinate of each relative minimum of f on the interval -2 to 3. So for relative minimum, the way we typically justify a relative minimum, and this is not going to be an exception, so we will follow this approach, is to show that f prime, and if it's a minimum, your function decreases, then increases, which means you have a negative slope. So f prime must change from negative to positive at a critical number. Okay, so that's our game plan. And so we are looking for any places first where we have a critical number from -2 to 3. And so f prime equals 0 twice on that interval. Happens once at -1, happens again at +1. And then I am now looking for a place where f prime changes from negative to positive, and that happens only here. At x equals 1, the value of f prime is 0, therefore it's a critical number, and the derivative changes from negative to positive. So there it is. So I would say f prime of 1 is equal to 0, and f prime changes from negative to positive at x equals 1. Therefore, a relative minimum or local minimum, however you want to do that, at x equals 1. And so there's your justification and explanation for 1. And the way they worded this, they said find the x-coordinate of each relative minimum. They said find the x-coordinate of each relative minimum, not is there a relative minimum. So the way it's worded tells you that one will exist, and that's kind of a nice thing. And they do the same thing on part B. Explain why there must be a value c for which f double prime of c equals 0. They don't ask you to determine if it happens. They tell you it happens. We just have to explain why. Is that needed? I thought you'd be happy over there eating your snack. All right. So the fact that it does happen helps. And this one, it's a little bit unique. I'm going to use the mean value theorem because we're trying to establish the value of a derivative. This one happens to be the second derivative. So I'm going to use the mean value theorem, which typically says that on a differentiable function, f prime of c must equal f of b minus f of a over b minus a. But you can really apply the mean value theorem between any function and its derivative. So if I just want to add an extra layer of derivatives here, this will also work for the second derivative if you find the slope of the first derivative. And so that's what we're going to do here. Now we do know that f is twice differentiable, and because f is twice differentiable, that means that f prime is differentiable, and anytime you cite a theorem, you absolutely must establish the conditions that allow you to use that theorem. If a function is differentiable, including the derivative, if the derivative is differentiable, therefore it is also continuous, and you absolutely must also write continuous as well as differentiable. So f prime is differentiable and continuous on the interval. We are focusing on -1 to 1. Therefore, the mean value theorem says that f double prime of c must equal f prime of 1 minus f prime of -1 over 1 minus -1. And when you look at those values, f prime of 1 and f prime of -1 are both 0. And the fact that they are equal to each other is what will allow this to work. That is our justification. This is also Rolle's theorem, because Rolle's theorem is the very specific case of mean value theorem where the slope is 0. However, you can kind of forget Rolle's theorem and just use mean value theorem every time you're trying to establish the value of a derivative. Moving on to part C, they introduce a function h, which is ln of f of x, find h prime of 3. This one's going to be relatively quick. If you're going to find h prime of 3, you first have to find h prime of x, and the derivative of a natural log is the derivative of the inside, known as the argument, divided by the inside. And if that is h prime of x, h prime of 3 would equal f prime of 3 over f of 3, and both of those values should be in the table. F prime of 3 is 1/2. F of 3 is 7, and I would stop there. No point in cleaning that up or simplifying it in any way, which brings us to part B. They say evaluate the integral, not approximate. And if you are evaluating an integral, you must find the antiderivative first. And this one will be a u sub problem where we will let u be the inside of the f prime function. So u is g. My du is going to be g prime of x dx, and that is exactly what I have on the outside. We don't have to do any alterations to this to make the u sub work. So I'm going to go ahead and substitute that out. I always take care of my du first. I'm going to ignore the f prime of g first. I'm going to replace the g prime d of x with a du. I'm going to leave room for me to squeeze the rest. F prime of g will become f prime of u. And now don't write -2 to 3, because -2 and 3 are actually values of x. They are not values of u. So what I like to do is, oh gosh, really? F prime of u d. Okay, so what I like to do is convert my limits. And so if x is equal to -2 and u is g of x, then u equals g of -2. And at -2, my value of g is -1. So I'm going to go from -1. And if x is equal to 3, which is my upper limit, then that leads to u prime, not u. That means u is, geez, what am I doing here? Let's undo some stuff here. Okay, so if x is equal to 3, then u is going to equal g of 3. And looking at the table up here, at 3, the value of g is 1. So we're going from -1 to 1. Now we can compute the antiderivative of f prime of u, which will be f of u, f u, from -1 to 1. And then I will plug in my 1 and my -1 and subtract. I cannot stop yet because I still have to evaluate f of 1 and f of -1. You see, at 1, the value of f is 2. At -1, the value of f is 8. And now I can stop. However, this one's not too difficult to clean up to a -6. And there is your complete solution for number 5.